Hello, everyone.
Okay, can we start?
Sure, thank you. Hello, everyone. My name is Mohamed Assaf. I'm a PhD candidate in University of Alberta, Canada. Today, I'm going to present our paper, a digital twin-based computer vision system for monitoring model construction progress. So to start, the model construction has made great contribution to the Canadian construction industry. And according to the latest Model Building Institute report, the market share of model construction has reached 7.5%, which was almost double the value recorded at the year 2020. But we usually look into how we can increase this ratio from this 7% to a greater value. Through the literature, we identified a lot of obstacles that can slow the adoption of modular construction. Based on the frequencies, we have ranked these obstacles. We can see obstacles related to the limited manufacturing capacity, the coordination problems, the poor integration between the supply chain stages, and all of these challenges contribute to the deviation from the actual schedule of model construction to the from the planned schedule of model construction. In this sense, if we rely on the fixed schedules, we will most likely face the deviation. And according to the literature, to have better monitoring of model construction progress, we need to have tracking of the interconnected processes. We need to have effective communication. We need to have integration between the supply chain stages. We need to have dynamic scheduling, alerts for the delays, and so on. To this end, this paper
to the site and rapid assembly. This technology already gained significant traction in many countries like UK, Singapore, China, and Australia. By leveraging highly standardized designs and factory-based production, modular construction not only supports the green and sustainable construction development, but also help the development of the construction effect. In Hong Kong, this technology is officially known as Modular Integrated Construction, or MIC for short. The government has been promoting MIC since 2017, primarily to tackle two pressing challenges: housing shortage and an aging construction workforce. And the result has been impressive. This method typically shortens construction cycles at 30 to 50%, while also significantly reducing labor cost. The widespread adoption of MIC is already reflected in a large-scale public housing developments, as well as the specialized high-rise structures, all of which benefit faster project efficient and enhance our own site safety. To give you a few project examples, such as the KU student hotel, and the Sunlight Market, and the primary school. So why MIC is promoted and adopted in Hong Kong in a large scale? Because the traditional construction industry is struggling with poor productivity, low quality, sustainability, and a complex production environment and low profitability. On top of that, we are facing a global and local housing crisis, a shrinking skilled workforce, and material shortages. So MIC can address all of these challenges head on. So we can introduce our research aim and objectives. The overall aim is to use static-based models to calculate the reliability of modular building systems. Specialized, we want to capture the uncertainty and the dependency within the building systems to predict the failure mode and the degradation process. And to achieve this, we have broken the work down into three main objectives. First, we classify the subsystems of a modular building and develop models to describe the degradation process of the MIC buildings. Second, we identify the main failure mode in MIC buildings. For each mode, we look at the associated system and the failure indicators and the types of failure. Finally, we collect the real-world data to estimate the world parameters. First, we divide the subsystems performance into two types, structural and non-structural. Non-structural parts degrade faster but may have minor failure consequence. Structural parts degrade slower but may result in more severe failure damage. We focus on three critical structural subsystems. First, module structural components. That's the boxes including frame, slabs, and walls. Second, the inter-module connections, which bring the boxes together. And the third, load transfer zones, which transfer the zone load to the foundation. Then we define a clear state space to map the component's health. We break the continuous deterioration process into discrete observable status from S0 intact to S4 failure. And S4 failure state is an absorbing state. It means once it's reached, the model stays there unless restorations. The left feature shows the three structural subsystems degrading independently, each with their own status and transitions. But the structural subsystem can be interrelated. So the deterioration rate of each subsystem adjusts based on the health of each other. The primary dependency is how modular structural component states affect the intermodular connection deterioration. And there are also secondary feedback effects. Connection conditions stress the modular themselves, captured by alpha IM, such as. And load transfer zones can amplify the connection deterioration through FLI. So finally, we can define the system failure as both MIC or IMC reaching or exceeding a severe degradation stage, such as S3 state. So we collected the real-world data to show the baseline transition probabilities of each subsystem. This is a simplified model. Each subsystem can only move to the adjacent state with no jumps. And that's why all entry outside the diagonal are 0. And the last table is subsystem dependency factors. Also, we can call it amplified factors. There's a quick note. MIC in Hong Kong is still young, under 15 years. So our data largely come from traditional buildings and factory tests. So the actual application will need further on-site calibration. So the left figure is the evolution of system failure probability. It shows that the system failure probability rises gradually at first, then accelerates sharply after 25 or to 30 years. And if we ignore these interactions, we are underestimate the long risk by about 1.6 times at the year 40. And the right three figures are the sensitive of analysis of a dependency factor. It shows that the alpha MI are the strongest impact, and overall, the uncertainties in subsystem interactions are not isolated degradation and dominated the long-term reliability. So the next step is such as